Let's tune the telescope into galaxies being born. And oh my gosh, who ordered this? We're finding galaxies in the dark ages. For as long as scientific inquiry has delved into the origins of our universe, the prevailing explanation has been the Big Bang Theory. Countless studies and the collaborative efforts of thousands of scientists have reinforced this theory, providing substantial evidence for how the universe came into being. However, the landscape of science today is markedly different from that of the past. Technological advancements continually usher in new theories and perspectives, challenging what we once considered indisputable truths. In this evolving scientific landscape, where new discoveries reshape our understanding of the cosmos, Neil deGrasse Tyson has become a prominent voice. Now, a groundbreaking development has come to light. The James Webb Space Telescope has unveiled a revelation that calls into question the long-standing Big Bang Theory. This discovery involves the detection of a staggering 750 new galaxies, each of which defies our previous expectations of what galaxies should be like. By the way, the James Webb Space Telescope was conceived and designed to help us understand the origin of galaxies, so we shouldn't be surprised that it's forcing us to scratch our heads. Join us as we explore how the new images from the JWST debunk the Big Bang Theory with the discovery of these 750 new galaxies. Scientists have put forward the Big Bang Theory as the leading explanation for the origin of our vast universe. According to this theory, around 14 billion years ago, the universe came into existence through some sort of mysterious cosmic event. It's the ultimate birth story of the cosmos. The surprising nature of the images captured by the James Webb Space Telescope has challenged scientists' understanding of the universe's origins. The hypothesis that these images directly contradict is the Big Bang hypothesis, which has long been regarded as an unquestionable truth by the majority of cosmological theorists. These galaxies appear to be too small, too smooth, too old, and too numerous when compared to the idea of the Big Bang hypothesis. The small size of the observed galaxies entirely contradicts the expected behavior in an expanding universe. According to the hypothesis, as the universe expands, objects should appear larger with increasing distance. According to the Big Bang Theory, at the very beginning of the universe, all matter, energy, and the building blocks of the cosmos were compressed into an extremely tiny and highly concentrated point called a singularity, a point where infinite density exists. When we say infinite density, we mean that the matter and energy within the singularity were squeezed together to such an extent that their density reached an infinitely high value. The concept of a singularity comes from our current understanding of the laws of physics, particularly the equations of general relativity proposed by Albert Einstein. Within the singularity, all the matter and energy in the universe existed in an extraordinarily compressed form. The extreme density implies that an enormous amount of mass and energy was concentrated within an infinitesimally small space. While the space isn't much of a problem here, with so much pressure and density, you've got unimaginable heat. The temperature within the singularity would exceed any temperature that can be observed or reproduced in our current understanding of the universe. The energy stored within this hot, dense point was the seed from which the entire universe would unfold. Expansion marked the beginning of the universe as we know it. It was the origin from which everything in our cosmos came. After the initial singularity, the universe started the journey of expansion and inflation. This process occurred over the course of approximately 13.7 billion years, shaping the universe as we know it today. The expansion of the universe started with an extraordinary burst of rapid expansion known as cosmic inflation. During this phase, the universe expanded at an unimaginable rate, far exceeding the speed of light. It's like the fabric of space itself was stretching and stretching, taking everything within it along for the ride. Cosmic inflation played a massive role in shaping the large-scale structure of the universe. It smoothed out irregularities, homogenized the distribution of matter and energy, and set the stage for the subsequent formation of galaxies, stars, and other cosmic structures. As the universe continued to expand, the rate of expansion gradually slowed down. Even though the initial period of cosmic inflation ended, the universe continued to expand at a measurable rate. This ongoing expansion is known as the expansion of the universe or cosmic expansion. Scientists have observed the effects of this expansion through various observations, such as the redshift of light from distant galaxies. The redshift indicates that as the universe expands, light waves get stretched and shifted towards longer wavelengths, shifting them towards the red end of the spectrum. We'll get into the details of this later on. At first glance, the images of the new galaxies taken by the JWST look absolutely breathtaking in a good way. You can see hundreds of galaxies all in the same frame, and the sheer power in the photos is something you just can't ignore. But that's what things look like to the average person. For researchers, things are the total opposite. These pictures are surprising to say the least. They don't match what scientists thought they would see based on their theories. In fact, they're seeing way more galaxies than expected, and these galaxies are different in some surprising ways. They're smooth, smaller than imagined, and really old. All these surprises are causing a bit of a panic among the scientists. One paper even starts with the word panic in its title, so you know things are serious. The galaxies look nothing like what they're supposed to. The age of the observed galaxies seems to be incredibly strange. The JWST observations indicate the presence of galaxies that appear to be unexpectedly old, challenging the expected timeline of galaxy formation and evolution within the framework of the Big Bang Theory. Plus, there's also the fact that the abundance of observed galaxies is a lot higher than what it was supposed to be. The Big Bang hypothesis predicts a certain distribution and density of galaxies based on the expansion and evolution of the universe, but the JWST images show a massive number of galaxies, which raises questions about the accuracy of the predictions made by the hypothesis. There's also the fact that the smoothness of these galaxies is totally unexpected. The Big Bang Theory suggests that galaxies should exhibit irregularities and variations in their structures due to the dynamics of their formation and evolution. However, the JWST images reveal galaxies that appear unusually smooth, lacking the expected level of complexity and roughness. According to the Big Bang nucleosynthesis theory, while the expansion was happening, we basically had all the stuff that makes up our universe squeezed into an incredibly small volume. It was clear that matter could not survive in space like this, so something had to give. As the universe expanded and cooled down, transformations took place. Particles such as protons, neutrons, and electrons began to interact with light and energy in their surroundings. These interactions played a pivotal role in shaping the formation of matter in the universe. During the first few minutes after the Big Bang, there was a process called nucleosynthesis. This process involved the creation of lightweight elements like hydrogen and helium. The extreme temperatures and conditions during this phase allowed for the fusion of protons and neutrons to form these simple atomic building blocks. Hydrogen, the simplest and most abundant element in the universe, was formed primarily during this early period. Helium, the second most abundant element, also emerged during this time. These elements were instrumental in setting the stage for the formation of stars, galaxies, and more complex elements that would come later in cosmic history. The synthesis of these elemental building blocks was a significant milestone in the evolution of the universe. From a primordial sea of particles and energy, the early universe transitioned into a state where matter actually began to take shape. This process laid the foundation for the rich diversity of matter and the vast cosmic structures that eventually came into being. Now, the Big Bang merger theorists themselves anticipated observing galaxies that were mangled and scrambled due to multiple collisions. However, the JWST images present a different story. Instead of chaotic and disheveled galaxies, the images reveal overwhelmingly smooth disks and well-organized spiral forms resembling the galaxies we see in the present-day universe. This unexpected observation challenges the notion that mergers are a common process in the evolution of galaxies because it's clear that these new galaxies haven't gone through any of the hardships that you'd normally expect if you were following the Big Bang Theory. If there are actually just a few or no mergers happening out there, it becomes implausible for tiny galaxies to grow and become hundreds of times larger. This implies that these galaxies were never originally tiny to begin with. Along with it, the optical illusion predicted by the expanding universe hypothesis, where objects appear smaller with increasing distance due to expansion, also doesn't exist as astronomers have meticulously observed and mapped the cosmos. They have discovered a striking pattern: the clustering of galaxies and the overall structure of the universe. Galaxies tend to congregate gravitationally together in vast groups, clusters, and superclusters, forming intricate networks that extend across the cosmos. This observed large-scale structure aligns with the predictions made by the Big Bang theory. According to the theory, the universe began as an incredibly dense and hot state, and over time it expanded and cooled. As the universe expanded, gravity played a pivotal role in shaping the distribution of matter and the formation of galaxies. The gravitational effects predicted by the Big Bang theory are consistent with what we observe today. Gravity draws matter together, causing galaxies to cluster in certain regions and form in a filamentary structure that connects them. These structures reveal the cosmic web-like pattern of the universe. The presence of these galaxy clusters and the interconnected web of matter provides strong support for the Big Bang theory. The formation of galaxies and their distribution across the universe aligns with gravitational effects expected from the initial dense and expanding state posited by the theory. The clustering of galaxies, the cosmic web-like structure, and the distribution of galaxy clusters all come together to support the idea that the universe has evolved from a primordial state of extreme density and has undergone expansion over billions of years. Though it's clear that the JWST images are creating quite the stir, it's important to remember that science thrives on challenge and inquiry. The unexpected findings from the JWST offer a valuable opportunity to delve deeper into the mysteries of our universe. While the images may seem to contradict some aspects of the Big Bang theory, it's crucial for the scientific community to approach these discoveries with a spirit of exploration and open-mindedness. In the end, it's this very process of questioning, investigating, and refining our theories that drives our understanding of the cosmos forward. As we delve into these cosmic revelations, we should remember that science is a journey of constant evolution. The universe continues to surprise us, and each new discovery opens up new avenues for exploration. Whether these new galaxies challenge the Big Bang theory or offer new insights into cosmic formation, they contribute to the ever-expanding narrative of our universe. So, as we gaze at these stunning images and ponder their implications, let's embrace the excitement of scientific discovery and look forward to the next chapter in our quest to understand the cosmos. As we dive deeper into the ramifications of the James Webb Space Telescope's discoveries, it's essential to grasp how these revelations might influence future astronomical research and our broader understanding of cosmic history. The JWST's findings are not just about spotting new galaxies. They're reshaping fundamental questions about how the universe evolved. The telescopic data suggests that the early universe was teeming with galaxies that appear highly advanced, which contradicts prior models that predicted a gradual buildup of complexity over billions of years. This raises intriguing questions about the processes of galaxy formation and growth. The conventional model posits that small, primordial galaxies coalesced over time, merging and evolving into the large, complex structures we observe today. If these early galaxies were already well-formed, it suggests that our understanding of the timeline and mechanisms of galaxy evolution might need significant revision. To address these discrepancies, astronomers and cosmologists may need to explore alternative theories or refine existing models. One possibility is that the early universe could have experienced periods of accelerated galaxy formation, which might not have been predicted by the Big Bang theory alone. These theories would have to account for the rapid appearance of mature galaxies and the observed smoothness of their structures. Another avenue of investigation could involve reassessing the role of dark matter and dark energy. The Big Bang theory relies heavily on the influence of dark matter to explain the formation of large-scale structures in the universe. If early galaxies are appearing differently than expected, it might indicate that dark matter behaves differently than previously thought, or that its role in galaxy formation needs to be reevaluated. Additionally, the JWST's findings could drive advancements in the study of the cosmic microwave background, CMB, which is the remnant radiation from the early universe. The CMB provides a snapshot of the universe when it was only 380,000 years old and is a cornerstone of the Big Bang theory. Comparing the JWST's observations with CMB data might reveal inconsistencies that could prompt new hypotheses about the universe's infancy. Moreover, the detection of such a large number of unexpected galaxies might inspire the development of new observational technologies. While the JWST has already pushed the boundaries of what's possible, future missions and telescopes could be designed to probe even deeper into the early universe. These next-generation instruments might offer more insights into the formation and evolution of galaxies, potentially resolving some of the current anomalies. In parallel, these discoveries highlight the need for interdisciplinary approaches to cosmology. Collaborations between astronomers, physicists, and mathematicians could lead to innovative models that better explain the new data. For instance, theoretical physicists might work alongside observational astronomers to develop new frameworks for understanding the early universe's structure and dynamics. Furthermore, the JWST's images and data offer valuable insights into the formation of stars and other celestial bodies within these galaxies. Studying the stellar populations in these early galaxies can provide clues about the conditions and processes that prevailed during their formation. This, in turn, could enhance our understanding of the chemical enrichment of the universe and the life cycle of stars. Ultimately, the revelations from the James Webb Space Telescope challenge us to rethink our cosmic origins and the fundamental principles of cosmology. While these findings might seem to undermine established theories, they also represent an opportunity for scientific advancement. By questioning existing models and embracing new data, we move closer to uncovering the true nature of our universe. In conclusion, the unexpected discoveries made by the JWST serve as a reminder of the dynamic and ever-evolving nature of science. As we continue to explore and interpret these cosmic phenomena, we should remain open to revising our theories and expanding our understanding of the universe. Each discovery, no matter how surprising, is a step toward a deeper comprehension of the cosmos and our place within it.